In this problem, you need to find the equivalent mass and stiffness of the system using the energy method. The system is something like two identical slender rods, and for each of these rods, they weigh mass of m kg. So this is the rod number 1. Let's call it rod AB. This is connected with a rigid link. Let's consider the link as massless. To another rod, this rod is rod CD. Now this rod AB is connected to the ground with the help of a spring. The spring is having stiffness 3K, and the rod CD is suspended on to the ceiling with the help of another spring. This spring is having stiffness K. Each of these is pinned at different locations as shown in the figure. So the pinning location for rod AB is from L by 3 distance from the end A. The distance between the spring and the pin is again L by 3, and the spring and the end B is L by 3. So these are the different 2L by 3. This is the configuration. The angle that this angular displacement on AB, suppose a clockwise displacement is given, then let's call this angle as theta. Once you give a clockwise displacement to AB, that will produce anti-clockwise displacement to CD, and so it will also make an angle. Let's call this angle as phi. So this is the configuration. Okay. Let's consider the relationship between the angle theta and angle phi. So if you look at, you can easily find from the geometry that 2L by 3 times L theta equals to L phi. Okay, if you consider 2L by 3 from this pin location, that will be equals to L phi. All right. So in other words, you can say that phi is equals to 2 by 3 theta. Okay, this relationship we are going to use when we derive equations. So let's do this again. The kinetic energy of the system The kinetic energy of the system, that is T, can be written as equals to half IAB theta dot square plus half MAB V square. So M half MV square, okay, plus half. Now for the rod CD, again similar. So this is phi actually, plus half MCD V square. Okay. So for rod AB and rod CD, this is the kinetic energy. Now you know that the moment of inertia of each of these slender rods is 1 by 12 ml square. So then that is equals to half times 1 by 12 ml square into theta dot square as it is, plus half into MAB is M, and the velocity is given by L by 6 theta dot square. Okay, so theta dot is the so the linear velocity, so or the translational velocity is given by half of that distance. So the distance is equals to again L by 3. So this L by 3 distance is 1 by 2 times L by 3 will be L by 6. So that's how you get for the AB. Similarly for BC, it will be very similar to this. It will be from the hinge. So from the hinge, if you see, the distance will be equals to 2L by 3 into 1 by 2. Okay. So this is plus 1 by 2 1 by 12 ml square. Now the phi angle can be written as 2 by 3 times theta for the consistency, plus half mv square will be half m times, just like we discussed, 2l by 3 times 1 by 2. Theta dot square. So this whole thing will come out to be half 2 by 27 ml square times theta dot square. So this is the kinetic energy in the system, and this portion over here we can say that this is the equivalent IEQ which is required. Okay. Now moving on to the potential energy of the system. Very simply put, potential energy is equals to half kx square. So the spring will store the potential energy. So the potential energy V will be equals to half kx square. So the k in this case for the rod AB is nothing but 3k. Okay, and the distance or the x is equals to L by 3 from the pinned location. Okay, plus for the rod CD you will have half k, and then the distance from the pinned location of the spring is 2L by 3 times angle is phi in this case. So again replace phi by 2 by uh, by 2 by 3 theta. Okay, so this can be replaced for consistency sake 2 by 3 theta, and ultimately what you will get is 1 by 2 43 by 81 k L square times theta square. This portion over here is the equivalent stiffness of our system. Okay, so these are the two answers. One is the equivalent moment of inertia or the rotational mass of our system, and this is the rotational stiffness of our system using the potential energy.